A very warm welcome dear students and hope that you are doing great. Today on your demand I have prepared this video, and also if you have not yet watched the chemistry guess, you can check the link given in the description box below. Also if you have not yet joined the Telegram and WhatsApp channel, then the link for the same is also provided in the description box below. So let's start our today's topic. So that is actually we will learn today in this video regarding DL nomenclature, capital DL, small dl nomenclature, and also the RS nomenclature. So let's start first of all DL nomenclature, capital DL. So what is actually this? This is the nomenclature given to chiral compounds, that means those compounds which are optically active, right? And it is given particularly to the sugars and the amino acids. And first of all, you will remember that this DL nomenclature, it is not an absolute nomenclature. D and L nomenclature, it is a relative. It is a relative nomenclature. So relative, what do you mean by this? It means that it is actually compared with something. So there should be reference compound, there should be reference substance with the help of which we can decide whether our isomer is D or whether it is L, right? So for this, Fisher has given this, we are having glyceraldehyde. So this is taken as our standard. So this is standard molecule with the help of which you have to actually tell that whether it will be your D isomer or whether it will be your L isomer, right? Now in this D-glyceraldehyde, you can check out what is the difference here. So we are having OH group is on the right side, right? OH is on the right side here. So that means this is your D. When OH is on the left side of this chiral carbon, you can see here, this is the chiral carbon, right? So when OH is on the left side, this is known as L. So simply you will remember that in case of glyceraldehyde, it's used as a reference compound, right? So when OH is on the right side of the last chiral carbon, see this is not the chiral carbon. When you just do the numbering, this is the carbon number 1, this is carbon number 2, and this is your carbon number 3. Now this is the last chiral carbon, this carbon number 2, it is the last chiral carbon. So when OH is on the right side of this last chiral carbon, it is your D-glyceraldehyde, right? And similarly, when this OH, it is on the left hand side, LHS, right? Left hand side, last chiral carbon, you have to check the last chiral carbon. So same here, it's 1, carbon number 2, and then carbon number 3. This is actually the Fisher projection in which we have shown this. So when OH is on the left side, so this is your L. So this is the nomenclature given. So D is your that glyceraldehyde in which the OH group which is on the last chiral carbon, if it is on the right hand side, it is your D, and if it is on the left hand side, it is known as L. Now you have to compare all other sugars, all other molecules, all other amino acids with this glyceraldehyde. So glyceraldehyde, it is used as a reference. It is used as a reference. This is the reference molecule, reference compound with which we will compare all other molecules, right? So let's move ahead. For example, I have just given here, this is my mannose. Mannose is also a sugar, right? So this one is D mannose and this is your L. Now you can easily understand that why it is D, because this is your last chiral carbon. You can just do the numbering from here. So 1, 2, 3, 4, and this is the carbon number 5 and carbon number 6, right? So this is my D mannose. So now on the last chiral carbon, that is carbon number 5, you have to check out whether OH is on the right side or whether it is on the left hand side. So here it is OH is on the right hand side, so this is my D. This is my D isomer. And similarly here in this mannose, OH is on the left hand side, so definitely it will be your L mannose. So this is the way how you have to differentiate between the D and L. So nothing, they are just simply the isomers. D and L, they are just the isomers. It is just a nomenclature given to the sugars and amino acids. So just we are having glucose, fructose, mannose, lactose, all these are what? They are sugars. And when you just draw the Fisher projection formula, I hope you have already understood this Fisher projection formula. So we write it like this: the most oxidizing group, that is aldehyde group, it is written at the top, right? And then we write the other groups just like this. Now here you have to check the last chiral carbon. This is very important. So in D and L nomenclature, you have to remember the last chiral carbon you have to check. on the basis of which you can just tell whether it is D or whether it is L. So the last chiral carbon is this one, because this is not the chiral carbon. Chiral carbon is that which is actually attached to 4 different groups, 4 different atoms or 4 different groups should be there. That carbon will be known as chiral carbon. So you can check out this is my CH2 and OH. This is not the chiral carbon, this is the chiral carbon. So the last chiral carbon here, it has OH on the left hand side, so definitely it is your L mannose, right? I hope you have understood. Let's move ahead. So now we can summarize like this, that if OH on the bottom chiral carbon, that is actually the last chiral carbon, if it is on the right, so the sugar is D. And similarly, if OH on the last chiral carbon, if it is on the left, so the sugar is L. Now you can check out here, this is my D glucose and this is my L glucose. I hope you have heard this. We are having glucose, the glucose which we actually take from the market, that's the D glucose, right? D glucose. Now can you tell me, this D glucose, it is the only glucose which will provide energy in your body, right? Not the L glucose. So this is very important. D glucose provides energy in our body, but not the L one, right? So that's why these stereoisomers, they are very important. Now you can check out this is our glucose and this is the last chiral carbon here. Now OH is on the right hand side, so it's my D. Now here OH on the last chiral carbon, it is on the left, so it is my L. So you have to check the last chiral carbon. So here you will remember that you have to check the last chiral carbon, not other chiral carbons, right? Now let's move ahead. I have more examples. This is my erythrose. Now you can check out here, the last chiral carbon is this one, so OH is on the right hand side, it is my D erythrose, right? Now similarly here threose, this is my threose, so OH is here also what? It is also on the right hand side, so this is my also D. You have not to get confused here. OH, whenever it is on the right hand side on the last chiral carbon, so it will be your D, and whenever it is on the left hand side, then it will be L. So in both these cases, erythrose and threose, they are also your sugars, so you have to remember these are both D. Now let's move ahead. Next we are here having, this is my xylose sugar, right? Xylose, and this one you can see, this is the last chiral carbon which I have marked star. So OH is on the right, so this is my D. OH is here on the left, so this is my L. So this is D and L nomenclature. It is easy to tell which is D and which is L. Now you can remember that this D and L nomenclature, it's also applied in case of amino acids. So we can also apply this to amino acids as well as to the sugars we have discussed. Now this is my amino acid. You can check out here, we are having the amino group, NH2 group and carboxylic acid group. So this is my amino acid, right? Amino acid. Now here, if you have to remember that here it is not, we are not having OH group. Now how to differentiate? With the help of this NH2 group. If NH2 is on the right hand side, this is my D, just this is my D alanine, and NH2 is here on the left hand side, so this is my L alanine, right? So it is now very easy. So whenever any amino acid is given to you, you have to check if NH2 is on the right hand side, so that will be your D isomer, and if this NH2 it is on the left hand side in the Fischer projection formula, then this will be your L isomer. So this is in case of amino acids how we apply. So now you can check out here, so this is my amino acid, so NH2 is on the left hand side, so this is my L isomer, and here NH2 is on the right hand side, so this is my D. So this D and L nomenclature, it is applicable in case of sugars and in case of amino acids. Now let's see another one, that is actually small d and L. So first it was capital D and L nomenclature, now next is small d and L. Now these are actually what we called as, this small d, it refers to dextro and levo. So D stands for dextro, which is also represented by plus sign, and L stands for levo. Levo, it is represented by minus sign. So the capital D and L, that is something different, right? That is just given on the basis of OH group or NH2 group, right? Whether they are on the LHS or RHS. But here in case of small d and L, they are your optical isomers, right? One is the dextro rotatory, another is the levo rotatory, right? They are actually those stereoisomers, right, which are optically active. One is dextro, another is levo. So what is optical isomerism? I have written down here. You can just take the screenshot of this, that optical isomers, right, they are the two compounds which contain the same number, same kind of atoms, right? They have same molecular formula. So and bonds, that is the connectivity will be same here, but how they differ? So they have different spatial arrangement of the atoms, right, but which have non-superimposable mirror images. This is very important. So optical isomers, they should be non-superimposable with each other. That means their mirror images, they should not superimpose each other. I will just give the example on the next page. So each non-superimposable mirror image structure, that's called enantiomer. So these are actually enantiomers. So small d and l, they are your enantiomers. So if one is the dextro, that is plus isomer, another will be your levo. And this d and l, it is experimentally seen with the help of an instrument that's called a polarimeter, right? That's known as polarimeter. So let's check it out. Non-superimposable. Just this is my one of the compound. So this carbon is my chiral carbon. It's attached to 4 different groups. Let's say we are having group 1, group 2nd, 3rd and 4. Now if I just have a mirror, now what will be the mirror image? This will just look like this. This is the mirror image of the first one. This is the actual compound, and this is mirror image, right? Now you can check out here. If I just take this compound, as such in my hand and put on this, on its mirror image, what I will see, this 4th one, it will just come here. That means it will not superimpose on its mirror image. So they are known as non-superimposable mirror images. So whenever we have non-superimposable mirror images, so that compound will be optically active. So that will show the optical isomerism. So you have to remember that whenever you have any compound, actually it should contain the chiral carbon. Just if I am having like this, for example, this is my carbon and it's attached to 4 different groups, right? Let's say I'm here having the fluorine, I'm here having the chlorine, this is my bromine, and this is the iodine. Now this molecule, it contains the chiral carbon. So this carbon is my chiral carbon, which is attached to 4 different groups. Now if I just have a mirror, here, how it will look like? It will just be like this. That is, carbon was here, fluorine, it was just here. Now chlorine will be on this side. It will just look like this in the mirror, right? Bromine here, and here it will be now iodine. Now just tell me, if I just took this compound and place on this fluorine, it will just come on this fluorine, right? That means it will superimpose on this fluorine, but this chlorine, it will not superimpose on this iodine, right? Because here it's iodine and here it's chlorine. If I just took this molecule and place on this molecule, that means on its mirror image, then it will not get superimposed on it. So that means this is optically active. So such compounds are chiral, such compounds are optically active. And if now this isomer, it is my dextro, then this will be the levo. And it cannot be told theoretically, it is experimentally told with the help of, I told the instrument that is known as polarimeter. So with the help of polarimeter, we can tell which is dextro and which is levo, right? Which is plus and which is minus. I have just shown here the diagram. See actually how polarimeter works. In case of polarimeter, what we are having actually, first of all, we are having unpolarized light. So this is the light which is shown here. It is unpolarized. Unpolarized means it is a normal light which actually comes from the source, right? So let's say we are having a source which provides the light, which gives the light. Now this light is actually passed through Nicol prism. So Nicol prism, what it will do, it will see here the vibrations, right? They were oscillating in all possible directions, isn't it? Waves are moving in all possible directions. Let's say we are having light is made up of photons. So photons, they vibrate in all possible directions. But now when this light is passed through Nicol prism, it will just give such a light which will be polarized light. Polarized means now the photons, they will vibrate only in one possible direction, as it is shown here. Now when this polarized, it is known as PPL, plan polarized light. So it was unpolarized light. First of all, any light coming from the sun or any source like bulb, that is your normal or unpolarized light. Now when we pass it through a Nicol prism, it becomes polarized. We are having plan polarized light. And when this plan polarized light, it is we are having this and we are passing it through the solution of any compound, then if the compound is optically active and if it rotates it towards the right, that means in clockwise direction, right? Just as it have been shown here. If the light rotates, if the PPL light it rotates towards the right, that means in clockwise direction, so then it is known as then it is known as dextro. So this is your dextro isomer. It is represented by small d, or you can also represent it by plus sign. So this is small d. So it is totally different from the capital D and L nomenclature. Now similarly, if I just pass this PPL, plan polarized light, through the solution of any compound, and if that compound rotates this PPL light towards the left, you can see this here. So PPL light, it has been rotated towards left by this compound. So this compound will be your LEVO. So this is your LEVO, that is, it will be represented by small l or minus sign. So one is your dextro, another is LEVO rotatory. So that means LEVO rotatory, it will just rotate the plan polarized light towards anti-clockwise direction. Anti-clockwise direction, right? So you have to remember this. So one will be dextro, another will be LEVO, right? And you have to remember that this D and L, it cannot be just told on the basis of the structure of the molecule. It is experimentally found with the help of instrument that is called the polarimeter, right? Now I will just give the example. For example, this is my lactic acid, right? This is the D lactic acid, small d. Small d means positive. Positive means, that means if this lactic acid, if it is put in the polarimeter, then it will rotate the plan polarized light, that is PPL light, towards the right in the clockwise direction. That's why it is your dextro isomer. And now if I just have this mirror, and this is the mirror image of this, then this lactic acid, that means this one, it will rotate the plan polarized light towards left, that means in the anti-clockwise direction, just like this. So this is my L, and it is your minus isomer. So one is plus dextro, another is small l, that is the LEVO, that is another. So this is one enantiomer, this one is another. So these are enantiomers. Now you can check out here, this carbon, it is your chiral carbon. So any chiral compound is optically active, right? Usually all those molecules which have a chiral carbon, they are optically active. Actually, in order to be optically active, you have to remember that it should form non-superimposable mirror image. For example, if I just took this compound and put on its mirror image, what you will see, this COH, it will just come on this COH, but here we are having methyl. So here we are having hydrogen, so methyl will come on this hydrogen. So that means they will not superimpose. So these are non superimposable mirror images of each other, and these are called enantiomers. So they are enantiomers, and enantiomers are optically active. So you have to remember this. Now let's move ahead. Now you can check out this is my carbon, as I already told, fluorine, chlorine, bromine and hydrogen. So it's attached to 4 different groups. So this is my chiral carbon, and if I just have mirror here, this will be a mirror image, and they are non-superimposable. So when they are non-superimposable, that means these are your enantiomers. And when they are your enantiomers, then you have to remember, if one is let's say dextro, another will be the LEVO. So that means if one will rotate the plan polarized light towards right, another will rotate the plan polarized light towards the left. And we cannot tell this just on looking this molecule. We can only tell it is just told experimentally. When we just put this compound in the polarimeter, then we can say whether it is dextro or whether it is LEVO. This is very important. Capital D and L, you can just tell which is D and which is L just by looking on the molecule. If OH is on the right, that is dextro, right? But here it is not like that. It is not like that. You can tell only which is dextro, which is LEVO, when you just put it in the polarimeter. So it is experimentally found. This is very important point to be noted down here. So you can check out this is my butanol. So you have to remember that this butanol, it will show optical isomerism. It's optically active because carbon is attached to 4 different groups. So this is my chiral carbon, and if this, let's assume this is my LEVO, then definitely this will be, it is dextro. So that means if this compound, it will rotate the plan polarized light towards left, let's say, then this will rotate towards the right. So these two are enantiomers, they are optically active. One is dextro, another is the LEVO. So they are just types of optical isomers, dextro and LEVO. And now you can also understand this by taking this example. So just we are having 2 hands, right? We are having left and right hand, right? So this molecule, it is just if I just put here the mirror, right? Mirror, how it will look? It will just look like this. So just if you are having your right hand, if you will just show it to the mirror, then that will look like your left hand, right? So that is the same is the case. That's why this we called as non-superimposable mirror images. Just your right hand, that is the non-superimposable mirror image with its left hand. So same is the case. For example, if this compound is your dextro rotatory, then this one will be the levo. So if it rotates the PPLI towards the right, then it will rotate towards the left. So I hope that you have understood this. Now let's move towards the very important, that is the RS nomenclature. Now RS is very important. It's also, as I told, D and L, that was the relative configuration. This R and S, it is the absolute configuration. That means in case of D and L, we were taking the reference compound, and that was the glyceraldehyde. We were comparing all other sugars and amino acids with the glyceraldehyde, isn't it? That was the relative configuration. But this R and S nomenclature, it is the absolute configuration. That means you have not to compare with any other reference compound. It is just the absolute. There are some rules which were given by Can, Ingold and Prelog, which are known as CIP rules, right? There were the 3, Can, Ingold and Prelog. So they have given some priority rules, what we call as CIP rules. You have to remember these. For example, the first rule is atomic number. For example, let's say this is my carbon and it's attached to 4 different groups, right? Let's say we are having the fluorine, we are having the chlorine, we are having the bromine and iodine. Now I have to just give the priority. These are the priority rules. That atom or element which has higher atomic number, right, that will be given high priority. For example, we are having iodine. Its atomic number is very high as compared to fluorine, chlorine, bromine, so its priority will be 1. And then we are having priority number 2 to this bromine, and 3 to this chlorine, and 4th will be to this fluorine because it has very low atomic number. So first of all, more the atomic number, more will be the priority. Higher the atomic number, higher will be the priority. Now if atomic number is same, then we have to check out the mass number. For example, let's take another example. Let's have here we are having deuterium, we are having the protium, hydrogen, isn't it? Let's say we are having here CH3 methyl, right? And now we are having, let's say here CH2 and CH3 ethyl group. Now how to give the priority? Now here you will remember that hydrogen and deuterium, they have atomic number 1. Now what we will do? We will just move towards the mass number. So its mass number is 1, deuterium mass number is 2. Higher the mass number, more will be the priority. So priority will be higher to this deuterium as compared to this protium, right? So for example, if we are having tritium, right? Tritium, it will be having high priority than deuterium and then the protium, right? This will be the order because all these have same atomic number, but the mass of tritium, it is very high, right? So higher the mass number, higher will be the priority. It is in case of isotopes, you will apply this. Then we have to also remember next atoms. Now what is this? For example, see here it is the carbon, atomic number 6, mass number 6. Here it's also the carbon, atomic number 6, mass number 6. Then what you will do? You will just move to the next atoms. For example, here next atom is carbon, hydrogen, hydrogen, but here it is hydrogen, hydrogen and hydrogen. So all the 3 are hydrogens, so its priority will be low. But here we are having carbon, then we are having hydrogen and hydrogen, so the priority of this will be very high. So first priority will be, I will write with this red color. So first priority will be to this ethyl, second priority will be to this methyl, and then I told higher the mass, higher will be the priority, then it will be third priority to this, and this will be having fourth priority because it is having atomic number 1. First you have to check the atomic number, right? Then you have to move to the mass number, then to the next atoms, right? If you are having, if first atom it has, we cannot decide priority. If on the basis of first atom we cannot determine the priority, then we have to move to the next atoms, right? I hope you have understood this. And then similarly we are having double and triple bond. You have to remember that double bond, it is treated as 2 separate bonds. Just we are having this double bond, so it is considered like this, that these are 2 separate single bonds, just like this. And similarly, if you are having the triple bond, let's say carbon carbon triple bond, then you have to consider it like this. That means these are just three single bonds. Triple bond is considered as 3 single sigma bonds, right? Then if we are having atom and lone pair, for example, if I am having nitrogen, so it has here lone pair on it, and we are having here, let's say, hydrogen. So which will have more priority? if I am just considering this, atom will have more priority as compared to the lone pair. I'm just taking only these in order to compare. So lone pair and atom will have higher priority as compared to lone pair. So these are the CIP rules. So I will again repeat. One is the atomic number. Higher the atomic number, higher will be the priority. Now if we are having isotopes, they have same atomic number, then we have to consider the mass number. Higher the mass number, higher will be the priority. And then if two atoms which are connected to the chiral carbon, if they are having same atomic number as well as same mass number, then you have to move to the next atoms. For example, here in case of ethane, next atom is my carbon and 2 hydrogen. So carbon, it has high priority, so we will give it priority 1 here, and in case of methyl it will be priority 2. And similarly, if we are having double and triple bond, they are just considered as 2 single bonds and 3 single bonds. And whenever atom and lone pair is there, so atom is given higher priority than the lone pair. Now see it here, what we have to do then. After we have just assigned the priority, for example, just you can check out here, it is chlorine, right? It is here OH and methyl. So chlorine, its atomic number is very high, so it's having priority 1, and then oxygen 2, then carbon 3, and this hydrogen, it will get priority 4. Now what we have to do then, just see here, this priority 4, you have to neglect this just as it is not there. For example, you will just draw it like this. You will write here Cl, you will write here now OH, and here it is my CH3. Now chlorine, it's having priority 1, right? It is having priority 2 and 3. Then you have to rotate your I from priority 1 to priority 2 and then to the priority 3. You have to rotate your I just like this, and see how I rotates. So I rotates in this direction. That means this is what? This is the clockwise direction. Now if I rotates in the clockwise direction, then it is known as rectus or isomer. So or actually it has been derived from rectus. Rectus means towards right. You have to remember like this. Or stands for rectus. And then we are having sinister. Sinister means left. That means if I rotates in the anti-clockwise direction, then it is given S, and if I rotates in the clockwise direction, then it is given the name OR. So one is the OR isomer. So OR stands for rectus, which means right, and S stands for sinister, which means left, simply anti-clockwise direction. Now you can check out this here. Our I, it rotates when we just move from priority number 1 to 2 to 3. You have to just neglect this fourth priority group, which is at the bottom. So 1, 2, 3, it rotates in the clockwise direction. So this is my OR isomer. So it is having OR configuration as shown here in the diagram. Now you can check out here, it's my priority 1, 2 and 3, and I rotates in the anti-clockwise direction, right? It is just like this, anti-clockwise direction. So that means it will be your S configuration, sinister. So let's move ahead and solve more examples. This is the one of the enantiomer given here. This is the priority number 1, 2 and 3. As I told that higher the atomic number, higher will be the priority. So 1, 2, 3. Now how I rotates? 1, 2 and 3. 1, 2 and 3. So I rotates just like this, 1, 2 and 3. So that means our I rotates in the anti-clockwise direction, that is left, that is sinister, S, right? Now here it's mirror image. If we check out, in case of mirror image, if we just give the priority to the atoms, then you can check out 1, 2 and 3. So that means how it rotates in the clockwise direction. So that's your R. So this one is your R, and its mirror image, that is this one, left one, this is your S, and this mirror image, it is OR. Then let's see another one. So here you can see OH, it will be having given higher priority 1, then 2 to this ethyl, and 3 to this methyl, and 4 will be the hydrogen, right? So from 1, 2 to 3. So when you just move from 1 to 2 to 3, how it your I rotates? It rotates in the clockwise direction. So that means it is your rectus or isomer. And similarly here you can check out 1, 2 and 3, it I rotates in the anti-clockwise direction, just like this, anti-clockwise direction. So that means it is your S enantiomer. So I hope you have understood. So you have to just remember these rules and you have to apply them. For example, now this is very important because this is the Fisher projection. Now in case of Fisher projection, there is one important rule which you have to remember, that is if the fourth priority group, you can note down this, that if fourth priority group, it is on vertical line, if fourth priority group it is on vertical line, then there is no change. That means if I rotates in the clockwise direction, then it's R. If I rotates in the anti-clockwise direction, then it's your S. Now let's check it out here. We are having 1, 2 priority, 3 priority. You can give the priority because oxygen, its atomic number is high as compared to carbon, so its priority will be 1. Now check out here, it is here carbon. So what you will do, you will just move to the next atoms, right? But here aldehyde, you can just represent it like this. It is C double bond O and H. As I already told that double bond is treated as two separate single bonds, so you have to write it like this: single bond O and then again single bond O, and then we are having here H, right? So it is O and H. You can write it here O and H, oxygen and hydrogen. But here now to this carbon we are having oxygen and 2 hydrogen, so you will write oxygen, hydrogen. So which will get more priority? Definitely this one will get second. So 1 priority to OH, second priority to this aldehyde group, third to this, and hydrogen will get the fourth priority. This is the Fisher projection, right? Whenever we write the Fisher projection, I told there is vertical line, this is the vertical line, and this is the horizontal line. Now what I told, if fourth priority group is on vertical line, if it's on vertical line, then there is no change. That means but here you can check out that this fourth priority group is not on the vertical line, it's on the horizontal line. Then you have to change. So if you will remember, if fourth priority group is on horizontal line, then what you have to do, if it comes S, then it will be your R. You have to tell the opposite. If you are having R configuration, then it will be your S. This is very important. Now check out here, you can easily tell here. Now you can see that on rotating our eye from first priority, then second, then third, isn't it? 1, 2, 3. How our eye rotates? Eye rotates just like this. That is which direction it is? It is anti-clockwise, right? This is my anti-clockwise direction. So anti-clockwise means it should be S, but it will be our R. Why? Because fourth priority group, it is on horizontal line. You had to remember these two rules. They are particularly for Fisher projection. The earlier examples which I have told, they were not in the Fisher projection, but this is in the Fisher projection. So whenever we have Fisher projection, you have to remember, if the fourth priority group is on the vertical line, then no change. But if the fourth priority group comes here or here, that means on the horizontal line, then we have to reverse. If it comes out to be S, then it will be R. If it comes out to be R, then it will be S. So this one will be your R. It will not be S, it will be R. I hope you have understood. Let me give the next example. Next is this one. See, this is having priority 1 and this is having priority 2 and 3. Now how you will rotate? From 1, you are having here 1 priority and then 2 and then 3. So our eye rotates like this. That is the clockwise direction. We are having just like this clockwise direction we are having. So clockwise means rectus. Rectus means R. Rectus means R. Now here you can see that the fourth priority group, it is on the vertical line, so definitely it will be your R. It will be your R, right? But if I will write the same like this, for example, I am having here the hydrogen, let's say I am having here the CH3, let's say I am here having the OH, right? And let's say I am here having the ethyl, ET is the ethyl. So the higher priority, it will be 1 to this OH, 2 will be to this ethyl, 3 will be to this methyl, and this will be the fourth one. Now if you just rotate here the eye from first priority, then second, then third, you can check out, it comes out to be, our eye rotates in the anti-clockwise direction, that is sinister. And this will be your sinister. Why? Because fourth priority group, it is on the vertical line. It is on the vertical line, right? It is on the vertical line. Now let me here give you the examples, and you will just tell me which is R and which is S, isn't it? For example, if I just write here, this is in the Fisher projection. We are here having the H. Let's say here it is the chlorine. Let's say it is here the bromine, and let's say here it is the methyl. You have to tell me whether it is R or whether it is your S isomer. Then the next is like this, that is, it's my CHO, and here it's my CH2OH, and it's my OH here, and it's my H here. You have to tell whether it's R or S, and then you will just comment the answer in the comment section below. And if there is any doubt, you can let me know in the comment section. This is my ethyl here, and this is my methyl here, and this is my SH here, and this is my OH here, right? You have to tell whether it is or whether it is S. Similarly, you can also tell me whether you have to tell me here that whether it is or S. So here it is fluorine, chlorine, and here is the deuterium, and here it is the tritium, right? Next is like this, where here having COOH, I am here having the fluorine, here is the chlorine, and here is my let's say it is my OH. And next molecule which you will try, that's like this, that's I am here having COOCH3, it is the ester group, fluorine here, and here it is the chlorine, and here it is the hydrogen. So I hope you have understood the DL nomenclature, capital DL, small dl, and RS nomenclature. Now if there is any doubt, you can comment in the comment section below. Also you can join the Telegram and WhatsApp channel from where you can get the latest updates. Thank you for watching.